So hello everyone. It is the third race online seminar for 2021. Today Stefanos will present data analysis and visualization, extrasensory dataset, topics on human activity recognition. You're ready.
Hello everyone. Today I'm going to present you an exploratory analysis of an open dataset called Extrasensory for human activity and context recognition. The extrasensory dataset enables research and development of algorithms and methods related to human activity and context recognition. Additional information is needed to recognize more complex and diverse activities being performed from different users. Smartphones and smartwatches through activity recognition have enabled the development of various personal and personal assistance applications, monitoring elderly people, as well as recommender systems for places and locations. The dataset published by Weisman et al. Is a result of a user experiment they conducted with 60 participants using sensing devices and collecting data from different sensors such as accelerometer, gyroscope, magnetometer, location, and audio, among others. Additional to sensor measurements, they asked from their participants to provide them labels of their activities, their locations and situations throughout the participation period. The reasons I chose to focus on this dataset, apart from its large scaleness and the variety of the sensors, is that the data were collected in real-world settings, providing in this way a more realistic picture of a person's daily life, including more complex activities and promoting real-world applications. Nowadays, a common approach to collect sensor data from sensing devices, as well as to acquire labels from the participants, is to develop an application that activates the sensors of the smartphone and enables the participants to provide appropriate labels. For this purpose, the authors developed an app that collected 20 seconds of measurements in each minute. And in order to obtain the labels, the app offered 4 different mechanisms. The active reporting, with the active reporting, the participant can select the label that will be relevant in the near future for a specific amount of time. With notification, the participant periodically receives a notification asking to report the label. With the label selection, the participant selects manually the label from a menu with predefined labels. And with history view, the participant can select a label that has been selected in the past. And in order to ensure that the experiment would be as close as possible to real-life conditions, the researchers applied 4 conditions for the data collection. First, they used smartphones and smartwatches, as these devices are widely adapted, offering familiarity and comfortability to the participant. Second, they did not constrain the device placement, allowing the participants to carry their smartphones in any way convenient to them. Third, they did not instruct the participants where to perform the activities, and the participants were free to visit places based on their daily routine. And lastly, participants performed their activities without any script or task targeting specific activities. Again, the reported activities came from the user's daily routine. Applying these conditions and without any direct observation or monitoring of the participants, the experiment faced some issues during the collection. These issues are quite common for experiments conducted in real-world settings. To name few, usually participants tend to turn off sensors, either for private reasons, either to avoid battery drain. Participants tend to forget, get bored, or being unable to label, report labels on specific moments. Also, they do not always carry their smartphone or wear the smartwatch continuously. And they reported sensor malfunction or other technical or connectivity issues. The result of these problems is that the published data set includes missing values and unbalanced data between the days, the participants, the sensors, and the labels. Starting from the users, we see that the data collection days vary from 4 to 15 days. And some of them provided an extensive number of labels, while others provided significantly less labels. Additionally, we see that there is not a significant correlation between the number of days and the number of labels. The dataset contains 51 different labels, including physical activities, daily living activities, social interactions, environments, and phone positions. It's worth mentioning that there are labels that have been reported simultaneously, meaning that for each minute, the participant reported more than one label, allowing to construct combinations of the labels for multi-label approaches. Previously, I mentioned that the dataset is unbalanced. I think this graph shows exactly that. As we see, the most frequent labels were the label of indoors, home, sitting, the phone on the table, lying down and sleeping, where some of the labels like singing or doing laundry have very few examples. This imbalance could be due to some common activities that most users share, and that each user can have different daily routine engaging in different activities that are not so common. Moreover, the sample size and the duration of the experiment probably is not sufficient to have a clear picture of the daily routine. Getting into more detail, we see that within the whole dataset, more than half of the labels contain null values. Almost 40% contain zeros, and a small percentage contains ones. The ones state that the label is relevant to the specific minute. The zeros that is irrelevant, and the null values represent uncertainty, as it's not clear if a specific label is relevant or not in a specific minute. Likewise, in terms of days, we see that in some days the participants reported much greater number of labels than other days. Probably this could also be to the daily routine or the mood of each participant on specific days. As I mentioned before, some of the labels were reported at the same moment. This matrix reveals some of the co-occurrences of the labels. For example, sleeping with lying down were frequently put together, running and bicycling with exercise, and bathing with standing, computer work with sitting, and so on. Most of the combinations are based on common sense, but this information could be helpful to have better results in identifying the most frequent combinations, as well as recognizing activities based on location and phone position or vice versa. The phone position itself can provide cues about the user's activity. When the phone is on the table, it's more likely the user is doing hand activities than walking or shopping, where the user most probably has the phone in the pocket. The phone position also gives us indication that in activities like sleeping or washing dishes and watching TV, where the smartphone is on the table most of the times, the smartwatch could be more useful for the recognition task. The same applies with the location or the environment where the activities take place. Some activities are more likely to happen at home, others at school, work, or at the gym. Whether sitting in a car or sitting at home is an information that we should take into consideration. Same as running outside or running at the gym. It's important whether it's possible to distinguish the activities based on the context for better decision making. Being able to identify the environment where the activity takes place, recognition systems could adapt accordingly. Now, regarding the sensor features, the dataset entails 225 handcrafted features from sensor and other modalities. And each feature can be defined as an element containing useful information for the data it represents. To obtain the features, the study applied several signal processing and statistical calculations from each sensor separately. Now, in the next few slides, I will show some visualization on few of the features and how the sensor feature values correspond to different labels. Based on two features from the accelerometer and the gyroscope, the time entropy of the magnitude signal of the gyroscope and the mean of the y dimension of the accelerometer, we get an indication of the values related to the phone position. We can observe that when the phone is on the table, the values of the gyroscope feature lies between 6.5 and 7. Now, based on the smartwatch accelerometer and between two features of it, we observe that most of the points on the watching TV label have the value 0 on the x-axis, but other than that, we cannot see any other indication. The mean of the magnitude of the watch accelerometer signal, we clearly see that sitting, standing, and lying down cannot be separated well. But in the case of running, we see that the values are higher on the lower quartile. Moreover, we can see a significant number of outliers, which is an observation that it needs further investigation to to identify what they represent. Before I conclude, I will mention a few works that used the extrasensory dataset to build the recognition models. The first one is from the authors that published the dataset. I'm using 6 of the available sensors and their features applied to logistic regression. They recognize 25 of the available labels with a balanced accuracy of 71.8%. The second work used only the accelerometer of the smartphone for a more computationally efficient system. They constructed 15 combinations of the included labels and achieved an 80% of balanced accuracy. The same approach has been followed by the next 2 works, with the difference that they included additional sensors and constructing further combinations of the labels, succeeding better results. Finally, the authors from the extrasensory dataset again, they built a unified model with a multi-layer perceptron using the same sensors with their previous work, and being able to recognize 51 of the combined labels with an accuracy of 77.3%. Concluding, I will get into the next steps I will follow is to get a deeper exploration of the features, as the basic observation is not enough and sufficient. And in order to get a better understanding of the correlation between the sensors, the features of the sensors, and the labels. Additionally, I'm considering to include the mood labels and the absolute locations that are available for some of the participants. Furthermore, I will have to define and focus on the approach and the methodology I will follow, and eventually to build an accurate recognition model for human activities. Thank you so much for your time, and I'm gladly to answer any questions.
Thank you very much, Stefanos, for the presentation. Do we have any questions from the audience for the participants?
I would like to ask a question, if possible.
Okay.
So thank you, Stefanos, for the presentation. I would like to ask, based on, let's say, the review of the literature that you have done, as well as the future work that you have potentially identified, what are some missing points or some future directions for human activity recognition, and specifically when it comes even to extrasensory dataset?
I think that they surpass the point that with the shallow machine learning techniques, and they have to get into the deep learning algorithms. Also, they're facing a lot of issues with the missing values, especially on the sensors, and they are trying to reconstruct the signals in order to fill the missing values. And also they mentioned that they need more data in order to have a better quality and quantity measures.
Thank you, Stefanos.
Also, I have a question. You say that you want to construct an accurate recognition model. Yes, do you have a focus, or just give data to the model and then the model will tell you whatever someone is doing?
No, I'm currently searching to. I'm currently trying to have to find a focus, and I'm in the process of it.
Maybe
I have
for instance,
just started like 2 weeks.
okay. Maybe for
Yes.
instance, it would be, let's say, interesting to differentiate between if someone is walking or running. I mean, if you have any focus like this or something else. But okay, if you are in the beginning, maybe you will
I'm still in the beginning. As you have seen, they started the first work. They did like a single label recognition, like they recognize each label separately. But then the future works, they try to combine the labels and recognize them on the same time, which is very interesting approach. But yeah, I'm still exploring how to proceed.
Okay.
Maybe I have a question about the algorithm. Say the some info you saw on the screen is focused only on some kind of simple algorithm. Why they don't use the other ones like ADA boost or the new one is XC boost? Because I think this combines many algorithms to find the best one. So, do you provide?
I'm sorry. Can you repeat that question? Can you repeat the question? I'm sorry.
Yeah, sure. Okay, focus on the algorithm column. You see, I saw from your screen is only show some simple algorithm like logistic regression, random forest. So why don't you use some kinds of boosting algorithm, combine the weak algorithm to choose the best one, like XC boost or ADA boost to improve the accuracy? You get my question? Did you get it?
Yes.
Okay.
Yes,
Did you
for
find
sure.
some
I
paper?
have to.
Okay, so sorry. Go ahead.
Yes, these papers they also investigated other algorithms except from random forest. They find that the random forest was
which year this
the best
paper published?
solution for their task.
Which year this paper published? Because
Excuse me?
when is published paper? When the author published this paper? Which year? 2020 or before?
It's 2020 and 2019.
Oh, really? It's still new.
They're quite new. Yeah, they're quite new. Yeah.
I want to apply some algorithm to recognize the activity of user, but I'm not sure which is the best accuracy because I want to deploy this in the limit environment. So thank you very much for your feedback. Okay.
Thank you.
I had a question or comment. I don't know what to say.
Andrei, is that you?
No, it's me, Vanjush.
Vanjush, your sound is very, very low.
Can you hear me now?
No.
Kinda.
Okay, wait a second. I'll switch off my my headphones.
Can you hear me now?
Yes.
It's pretty fine.
Okay. So because accuracy is not always the best way to measure the model general capacity for generalizing things, and I was thinking, what about, have you considered like using the area under the rock curve? I think that would tell you a lot more how good your method is rather than using a single metric as accuracy.
Yeah. The thing is, this is balanced accuracy. It's not accuracy. It's the sum of the true positive with the true negative divided by 2. And the thing is, the baseline system that the authors firstly developed, they used this metric, and consequently the others used the same to compare their models with them. But for sure, I will explore other metrics.
Yeah, because I think you don't have like perfectly balanced data set, do you? I mean, the number,
No, it's very balanced.
it's very balanced.
It's very imbalanced.
Okay, then yeah, that's one of the cases where accuracy, it's a very biased estimation of your general.
Yes,
I
yes,
mean,
but this is not the accuracy, it's the balanced accuracy. It's a different metric.
I mean, okay, maybe it's unbiased estimation, but I still, when I see the term accuracy there, I thought like it's because yeah, the area under the curve came for that purpose. When you don't have like
Okay.
unbalanced data, it tells you way more than just a single metric. As
can I ask a question? Can you hear me?
Yes, yes.
So basically, if I know correctly, if I remember correctly, like the balanced accuracy is basically an accuracy which is computed in a way that the true classes are balanced. So basically, you have it's the accuracy that you would obtain if you had 50% positives and 50% negatives, right?
I'm not sure about this. Of what I read on the papers, they used this metric balance accuracy because accuracy is biased.
Yeah,
So,
exactly, because you have imbalanced classes, and so basically you use the true positive rate, which is the probability, is basically the accuracy given the positive, and the true negative rate, that is the accuracy given the negative, and then you do the
divided by
average
2. Yeah,
between the two.
yeah.
So yeah, but I wanted to ask, like, what is the maybe Vanjus, because he raised the question, like, what is the difference between that, like, what adds the area under the curve rather than this like balanced accuracy? Because like I knew that once you have two positive rates and two negative rates, you basically have all the information that you need about about a model. And the precision, that and the precision.
Vanjus, if you want to answer.
yeah, I was writing down the because I attended your presentation a bit later than usual, than I should, because I was in a meeting. So the balance accuracy, it's a true positive plus
True negative, the sum, yeah, divided by 2.
It's basically 1/2 true positive rate plus 1/2 true negative rate to balance the two of them, basically.
Okay.
Of course, you can use any convex combination if you want to reach any like unbalanced accuracy, let's say.
I see, but I think the area under the curve, it's like if you change the threshold of your true positive and true negative, what's the threshold that if you vary this threshold and you plot the true positive versus the, I have to check it out because it's a long time that so you have to plot the true positive versus the true negative, and you have a curve there. And if it is like a totally random, it's going to be like a y equal to x is going to be just a straight line. And if it is a good approximation, then it's going to be something like with a big area under the curve. And I don't know if I can draw here. I can try to draw, but I don't think it's possible. But this one is just a single point in the rock curve, the balance accuracy. But the rock.
Okay. Yeah.
Yes, the ROC curve will give you all the different
On
situations.
the area, yeah.
Yeah, but I have a question for Stefanos. Like, do this paper just evaluate the balanced accuracy, or
No,
because normally
no,
they
they-
evaluate? Sorry.
Yes, tell me.
Normally, these kind of papers, when they evaluate balanced accuracy, they evaluate precision, then recall, that is true positive rate, and the specificity, which is true negative rate.
Yeah,
Do they?
Yeah, they did, but I just put the balance accuracy to compare between them.
Oh, okay, I see. Thank you. Yeah.
So, I wanted to correct myself that the ROC curve is false positive rate and true positive rate, and you plot them one versus the other. And in this case, when you have the confusion matrix, this balance accuracy is going to be just 1 point on the ROC curve.
Okay, so it's better the area under the curve.
Yeah, I mean, for me, it's kind of hard to follow without you know, with just without any visual or written.
I cannot draw anything. Can I try to share something? No, I cannot. I'll try to share a whiteboard. Can you see here?
Yeah,
Yes.
sure.
So this is the false positive, right?
Yes.
And this is the true positive. And then this is going to be from 0 to 1. 1 here, which is 100%. And if it is...
So you consider only the positives? You exclude the negatives?
Because I think in the confusion matrix, you have 100, they sum up 100% on both sides, right? And if you have the true positive here.
Yeah.
And then you have the true negative here, right?
Yeah, well, it depends on how you, like if you transpose it or not, but yeah, sure.
Yeah, it doesn't matter. So if you have one, you have the other kind of, because you subtract. How you do it? No.
False negative.
So this is going to be false positive.
Yeah, and above a false negative.
False negative. So this is true positive, I think. And then once you have one, you subtract 100% minus the other, and you get the other.
Yeah.
But so the idea is that with a balanced accuracy and with a balanced uncertainty, if your ROC curve is something like this, so ideally it should be like here, should be like, you know, something like this, and you get like very big area under this curve here. But if it is like something like totally random, you know, it's going to be like half the area. The area under the curve is going to be 1/2. It's going to be 1 multiplied by 1 divided by 2, because it's the area under this triangle here. And if you have like a good classifier, then the area under the curve is going to be very close to 1, because it's going to include everything, and it's going to be this this area over here. And that is going to be a very good model, because it doesn't matter what your threshold for classifying, you always get like a very good classification of your false positives, of your true positives, and intrinsic your true negatives. But if you have just a just a single accuracy metric, then it's going to be somewhere, I don't know, somewhere here or somewhere here. But that really doesn't tell how is the trajectory of your ROC curve. That's why you need the whole ROC curve and keep the area under it to tell the whole.
So basically, in a few words, if you take an accuracy score, you are considering one specific threshold. When you consider area under curve, be it the ROC curve or be it even the precision recall curve, what you are doing is that you are considering all possible thresholds and seeing at a different threshold how good your model is.
That's correct.
Okay.
And that's not a big problem, if I understand correctly, for like a good balanced data. It's not as bad problem as it is for imbalanced data. Because if you have like 90% positives and 10% negatives, right?
Yes.
You always get a true positive quite high value intrinsically. And that doesn't mean that your your model is very good. It's just like the data is much more positive.
But like actually the whole point of this balanced accuracy is, you know, to sort of like to rebalance as the data were like half positive and half negative. If you do the math, like it sort of works. The problem is that just one of the estimations is more rough than the other, but like.
Oh, okay, so it's like true positive plus true negatives divided by 2, right?
True positive rate. It's different. True. It's complicated. Basically, true positive rate is basically true positive divided over true positive plus false negative. Plus false negatives, and like the other is the complementary, and basically they represent one represents the probability. Like the accuracy given that you have a positive case. So if you restrict your probability space to the positive case, and the other is the accuracy if you restrict to the negative case. And so then if you average them, you are basically computing the accuracy. In the case you have a 50% probability of having a positive and 50% probability of having a negative. Yeah, I know. I mean, I know that it's harder to follow without like any equation or written stuff, but that's more or less it.
Okay, I will check it out because I never heard of it so far.
They're called the sensitivity and the specificity of the model.
Okay.
Check that out.
Yeah. These things have 1 billion name. Like they are called the recall, sensitivity, true positive rate. They're all the same thing.
Oh, is it from the precision recall curve, right?
No, recall and specificity. Like if you want to use those kind of terminology.
Yeah, but what I learned so far is that it's impossible to represent with a single score your model capacity.
Yeah, that's correct. That's correct.
It's no good.
Yeah, but yeah, I mean, of course, like every time you we reduce to one single score, you lose some information somehow. Like it doesn't matter. Like even with this area under the curve, you lose some resolution with respect to having like different metrics, of course.
So one single score is not ever sufficient. That's what I learned.
Yeah, exactly. That's what I was saying as well.
Okay.
It's nice to see us having a conversation and a whole discussion on these things. So do we have any more questions? Okay, as it seems not. So thank you very much, Stefanos, for the presentation, and thank you all for participating. We'll see you in the next Race Online seminar in 3 weeks.